Okay. Welcome back from the summer break. I hope you guys had a good time to relax. I certainly did. I took about 7 or 8 days out of town. We're talking about beach time, some water park time, some indoor relatives time. So I had a very good break. I've missed that for a few years now. So that was good. I am re-energized, and I hope you guys are too. Let us carry this energy through the end of the semester. After that, we get a couple of weeks again, right, before the fall starts. So, what are we talking about? We're talking about pipelining. Why are we doing pipelining? Because we want more with less. We have limited amount of hardware. We want to use that same hardware all the time. We don't want it to work on one instruction and it gets done. We don't want to wait. As soon as one resource gets done, one instruction uses one resource, we want to use the same resource for another instruction, right? That's what pipelining was about. But because of that, we ran into some problems. One of the problems was the write use data hazard. Write use hazard, what was that? You're writing to a register, and in the next clock cycle, you are using that same register, right? So that was a problem. Why? We were not ready with the correct value. In fact, we were not ready with the correct value for 2 instructions down, right? So we implemented a solution. There was a lazy solution with the NOPs, the no operations. The good solution, the more elegant solution, was register forwarding. So we did a XMEM register forwarding to solve the problem for the next instruction, immediately next instruction, after we do the write. And then we did the mem write back forwarding to solve the data hazard 2 instructions down from the instruction that we were writing. So that's where we were. That's where we ended things before the break. Now, this is going to be our last lecture on pipelining content before we get into memory. Memory is going to sort of get us to that bridge between computer architecture and operating systems. So pipelining, third and last. We're going to focus today on the load use data hazard. If I remember correctly, Bennett was observing this, while we were doing this write use hazard problem, he said, does it work the same way for load? Right? You said that, and it doesn't. So we have to talk about that specific type of data hazard, which is a load use data hazard, cannot be solved using register forwarding. So we need some other thing to solve this. And we'll also talk about the control hazard, which is based on branching instructions. What are the penalties? So essentially, instead of asking for permission, let's ask for forgiveness, right? So that we'll talk about how much forgiveness in terms of branching penalties later on. So 3 hazards. Structural hazard, that was what? Contention for the same hardware. We've not looked at that in a lot of detail. We've just left it at that. Contention for the same hardware. Same hardware cannot be used by 2 different instructions at the same time. Data hazard, we have spent quite a lot of time over there. What is that? Things are not ready, right? So this was the write use hazard. And today we are going to focus on load use hazard, which falls under the same category, data hazard, which is attempting to use an item register before it is ready with the new value. It still has the old value. Control hazard has to do with branching instructions or decision making. Attempt to make a decision before condition is evaluated, right? So for example, when you're doing a branch when equal or branch when not equal, you have to check the contents of the registers first before you can actually update the program counter appropriately. But the problem was that because we were doing pipelining, we were already running the next instruction. We had already put the next instruction into the pipeline before that condition got evaluated, right? So that was what we were doing. So what are the repercussions of that? We'll talk about that during branch penalties discussion. Some of the problems, like the write use hazard, was solved with register forwarding, write use hazard. write to a register and use that same register. Maybe we can make it this a little bit bigger. So add instruction, for example, and say you are doing something like this. Add $2, $1, $3. And then immediately use it, right? So subtract $4, $2, $3. You see, this has that problem. We cannot do this without register forwarding. We couldn't do this. But because we have register forwarding unit, where is that? Right here. We are able to solve this problem. We are able to execute this, update our $2 register, and then immediately use it in the next instruction. We are able to do this correctly with this. So some problems were solved with register forwarding. However, load use hazard cannot be solved here. This is the data path with the pipeline registers along with the forwarding unit. That's the block diagram for that. We have got your 5 stages. What were they? We had instruction fetch, instruction decode, execute, memory access, and then the write back stage. Right? Those were the 5 stages. And in the middle of those 5 stages, we had those 4 pipeline registers or pipeline buffers. The last 3 of them also have control signals on top of them. Why doesn't the first one have control signals? Because it has not been decoded yet. Right? So it has only after the instructions gets decoded, only then we generate all those control lines. That's what we will carry through. So this should be a repeat, right? Like this view should be something that we just like recap, like nothing new here. The key term here is what? Some data hazards, not all. The one type of data hazard we need to look at is the load use hazard, because the forwarding will not solve that problem. So let's see. Suppose you have something like this. These are a few instructions in that specific order. We are doing a load word followed by and or add and then set on less than. Now, if you look at this load word instruction, we are taking the base address from register 1, we are adding the offset of 20 to it, and that will be our target address in memory, from which we will load into register number 2, right? So we are changing the contents of the register number 2. Now, let's try to look at when is that ready? When are we changing the contents? When is it ready? Go through the instruction memory, which is the instruction fetch, do the register access, do the ALU. Why are we using the ALU here? To add these 2 guys, right? The base address and the offset. You read the data memory. Only after you read the data memory, you would have written the contents of whatever you just read onto this last, what is that buffer? That's your mem write back. Mem write back pipeline register, right? So you would have read the contents and you would have written it over here. That's when you know what will go on to $2, right? The contents of $2, you know them here. You don't need to write it on the register to know the contents. You know them after you read the memory. When do you need it? You need it over here. See, $2, your second register, you're writing to it, and then you're using it. Load use hazard. Different from the other write use hazards that we have looked at. How forwarding could have solved that. This one, forwarding doesn't solve that. Why? Because you need it earlier in time. For the previous ones, you were forwarding ahead. It was a feedback connection, but still you were forwarding ahead in time, indicated by the green lines, right? So as long as you are going in front in time, using it later in time, you're fine. But how are you going to do this? This needs it earlier, ahead of time. So I hope you guys agree that we cannot solve the load use hazard with register forwarding. Either type, the XMEM forwarding or the mem write back forwarding. Now let's dig a little deeper here. What can you solve? Look at the load word instruction, then look at the third instruction, or instruction. Is there a hazard, data hazard present over there? Look at this guy, load word, and this guy. Is there a data hazard over there? Yes, there is a data hazard over there because $2 is an operand here. Can you solve this with forwarding? Yeah? Can you solve this with forwarding? Sure. You have things ready over here. You need them over here. So you forward, indicated by the green line. You're good. Yeah? So what is that? What kind of forwarding is that? There are two types of forwarding, right? XMEM forwarding, mem write back forwarding. Which type is this? Good. Mem write back. So of course we are forwarding mem write back register. So by using mem write back forwarding, we are able to solve the data hazard for this instruction. Now how about the next one here? Well, there's no problem there anyway. There is actually. I just noticed that there is a problem with a different type of register here, right? It's not $2, $4 has a problem there. So what type of forwarding will help solve this? Same thing, right? Mem write back. So mem write back forwarding will solve this. So over here, you're solving two data hazards with mem write back register forwarding technique indicated by those green lines. However, there is a load use data hazard that we are not able to solve here. The specific one that we are talking about is the load word followed by the AND instruction. We are not able to solve that. Now, I want you guys to look at this, all 5 instructions here and think of a few ideas about how you could solve them without needing some additional hardware. No additional hardware. Can you guys think of solving the load use hazard? Go ahead. A no operation, right? So instead of this AND, I will use a no operation. Push everything down, use a no operation instead. Okay, so that will solve it, right? So that is one solution. But I hope Zach was a little bit hesitant to say that, right? Right? Because it was not the best solution. So any other? Look at all the 5. Look at this. 1, 6, 7. You're writing to $1, which is never a problem here. So idea, move this guy here and move everything down. So if you move that, rearrange the code, right? So if you have a complex, better compiler which can do this rearranging of code without changing anything, you could move this up and move everything down by 1, solving all the problems. So the load use data hazard or any data hazard that you may have, one way to solve that is in software by compiler rearranging the code for you. But we need something in hardware to do this. What are we going to need? Register forwarding unit cannot do it. So we need another unit to do this, which is what we are going to call the hazard detection unit. What is that going to help us with? The hazard detection unit is going to essentially just be responsible to detect the load use hazard. And if it detects the load use hazard, then it will essentially count that next operation out, do a no operation, do nothing in that. That's doing it in hardware. So let's see two things. One, when do you stall? Next, how do you stall? By the way, how many instructions do you need to stall by? One, just one, right? Like the next instruction is a problem. You don't have to worry about the instructions after that. We are just talking about one instruction getting stalled. For this specific load use data hazard, there are some conditions that have to be met for this particular thing to be, for you to judge whether this is the situation or not. The first thing is what? Do we have a load instruction in the execute stage? Go back and check. This is your fetch, decode. After you decode, what do you get? After you decode the instruction, you would have written all those things onto this. When I say all those things, what do I mean? I mean all the instructions as well as all the control lines on the IDEX pipeline register. And then if your load word instruction is in the execute state, how do you find out if it is a load or not? So the first thing that we need to understand is it a load word instruction or not? And one easy way to find out whether it's a load word instruction or not is look at the mem read control signal. Mem read control signal is one only for the load word instruction, right? That's the only instruction for which you access the memory and you're reading the memory. So that's the first thing. You look at this mem read. Look at the IDEX pipeline register. Look at the control signal mem read. If it is one, then you know what? This indicates what? If one, then instruction is load, right? So that tells us that the instruction in the execute stage is a load instruction. So that's one criteria, right? So we know it's a load. The next criteria we need to look at is the destination over here matching the source, one of the sources in the next instruction? If load is in the execute stage, then can I say that AND will be in the decode stage? Right, one stage behind, right? Like if load is in the execute stage, then AND at the same time will be in the decode stage or the register access stage. You guys agree with that? One back. So those will give us the next two statements. If this is the source, no, this is the destination. If the destination of load, we are still looking at the IDEX pipeline register. If the destination of load equals, what is this guy? This is the first source, source one of next instruction. In our case, it is the AND instruction. In our example, it's the AND. Is it equal to that or not? Or the other case, load destination equals the other source, source 2. Could be either one, right? Has to be a load, and it has to have that same register being written and then used. And if that is the case, we do a stall of the pipeline for one instruction. You guys see how we are going to implement the hazard detection unit? Okay, so if hazard detection unit is something that we are going to put together in hardware, then what are some of the inputs to that hardware? Can you guys think of some inputs to the hardware? Right. So all of these should be the inputs to the hardware, right? So imagine like a block in your data path to which you are getting something, mem read control signal. Where is that from? IDEX pipeline register. From the IDEX pipeline register, get register RT. From the IFID, get RS, and so on. Make all those connections that will go into the hazard detection unit. All right, so that was essentially what we are looking at, right? This is what we are going to check for. What are we checking for? If the instruction that is in the execute stage, mem read is 1, and there is a matching of source and destination. If those two conditions are satisfied, then we have a load use hazard. And we solve that by implementing that hazard detection unit. So let's try to see what all is happening here. You still have the forwarding unit. All of those elements are still there. Your 5 stages are still there. The 4 interstage pipeline registers are still there. Forwarding unit is there. Control unit is here. There is also an ALU control unit that is not being shown, but that is also here. We have included this additional hazard detection unit on top. Now, we have already discussed what are the inputs to that, right? The inputs to that, mem read, where is that coming from? It is coming from the IDEX pipeline register. That is an input to the hazard detection unit. We just agreed upon that. We also need RS, RT, depending on destination and source, from 2 types of interstage pipeline registers. One is for load. For the load, where is it going to come from? It is going to come from IDEX. For the next instruction, it's going to come from the IFID. Right, so you see this, where is this coming from? This came from here, right? Right there. Let me highlight in pink. What is that? That highlighted in pink is destination of load, right? What do we need to check that against? The source of the next instruction. Where is the next instruction? It's right here in the one before, the step before. How are you going to know whether it matches one of the sources or not? Well, look at the instruction. The instruction itself has those entries for RS and RT. Those are going to go here. So you are comparing, and you can clearly see that there are 2 arrows indicating RS, RT, one of the 2 operands. Right. So this is what I can say. This is source 1, 2 of, in our case, AND instruction. But in general, next instruction, the instruction following load. So inputs, mem read, load of, destination of load register instruction, sources of the instruction following that. Those are the 4 things that are inputs to the hazard detection unit. This has to be a 1. This has to match one of these, right? If that is the case, then you have detected a low use hazard. Outputs. There is an output controlling whether you need to write onto the IFID pipeline register or not. There is an output controlling whether you write PC or not. There is an output controlling a MUX, which is allowing all the control lines to go through as is, or a 0 to go through. So how do you stall the pipeline, right? Now we need to talk about how do you stall the pipeline. One is a no operation. For a no operation, all the control signals are a 0. So The moment you detect the load use hazard, make this control line such that 0 goes through everywhere. 0 here, 0 here, 0 here. There are 9 of these control signals, right? In the activity that you guys did, the last activity that you did, or the one before that, one of those activities, you actually wrote down all these 9 separate control signals. All of those are going to be zeros if you detect that load use hazard and you need to stall. So that's one. What about here and here? That you will simply select in such a way that you don't write. So you're not going to update your IFID pipeline register, and you're not going to update your program counter, which essentially means you're not updating it to the next instruction. You're just stalling the pipeline, getting done with 5 clock cycles. And after those 5 clock cycles get done, next instruction comes in, which is going to be what? And is going to come in. That's when you will update. That's when you will write to the program counter and start working on and. Because if it was one instruction later, right? Imagine this to be a not. And then imagine this, another instruction over here to be and. Will it be okay? Yes, we will still have write use data hazard, right? Because if this guy is here, we still have $2 here and $2 here. So we still have a data hazard present, but register forwarding will take care of that. One thing later is fine. One instruction down is a problem for load use. 2 instructions down, not a problem anymore. Go ahead. The no operation has to flush that throughout the pipeline, right? So whatever has come in into the pipeline, the and instruction, that has to go away. Now, all the controls and all of them have to be sort of goes to 0. After they go to 0, the next instruction, whenever it comes in, that's going to be your and instruction over here. So one has gone through, the next instruction has to come in through. So instead of starting here, now we are starting here. See that? Maybe I didn't understand your question properly. Right. So this one is out, right? So in terms of a pipeline diagram, this one is out, but this still starts here. So instead of starting at clock cycle 2, you're starting at the beginning of clock cycle 3. So in terms of a pipeline diagram, that is out. But in terms of starting, where are you starting? You're still starting at clock cycle 3. You still have that pipeline architecture. All right. We have that, deciding when to stall. How do you stall? Don't write to this, don't write to this. Make all of these 0. Everything else remains as is. Okay, other questions? Okay, next, we talked about this a little bit. Let's take a look at an example as well. Compiler can help. Complex compilers can rearrange the code in order to help with that instruction immediately after the load. So what you can do is this. In software, you can check for the hazard detection unit, right? The output of that hazard detection unit. If it detects a load use hazard, then you can attempt at rearranging the code. Essentially, remove the instruction immediately after the load to bring in an instruction that is independent of the destination of the load instruction, which is called a delayed load. So let's try to take a look at an example over here. We have a couple of load word instructions and a couple of store word instructions. Is there a load use hazard present over here? The red kind of gives it away, huh? There's a load use hazard, right? You're over here, you are writing to T2. And then immediately in the next instruction, you are using T2. Yeah? So there's a load use has. You guys agree with that? There's a problem? Because over here, what are you doing? Base plus offset, whatever is at that address goes into T2. Over here, what are you doing? Whatever is in T2 goes into that addition of address, right? So you're using contents of T2 immediately after you are loading into T2. So that's a load use data hazard present over here. Can you solve this without needing to stall? Compiler can help, maybe? What can you rearrange? What can you rearrange over here to fix the problem? Right. So if you switch these two guys, you're done, right? So this brings us to the trade-off. The trade-off is between what and what? Hardware complexity and software complexity. Over here, we are saying maybe the software can take some more responsibility of rearranging the code. Otherwise, you would have had to do it in hardware. Go ahead. You could have also switched the load words. Absolutely, yes. You could have switched these two guys, something into going to T2. Yeah, you could have also switched these two. Yes. Other option. Switch. This or this, right? So one of those two switches will do the job. All right. So where are we? Register forwarding solved some problems. Hazard detection unit takes care of the load use data hazard. Maybe we can offload some of the complexity to the compiler for rearranging the code. Next, let us come to the branch instruction. So the branch instruction, actually, you get into some really interesting situations with the branch hazard. Branch hazard is it's also, we have called it a control hazard, but it is also called a branch hazard. Essentially, we are attempting to make a decision about what? Which instruction to execute next? Is it the next instruction, or is it the instruction where we are branching, branch address, right? And it depends on what? The contents of two registers, whether they're equal or whether they're not equal. So we are essentially focusing on the branch when equal and branch when not equal. We will take a look at the branch when equal instruction as an example. So this is your data path with the control. 5 stages, 4 interstage pipeline registers. There's absolutely sort of no need to, again, talk about these things. One thing that I would like you guys to notice is this. There's a PC source control signal, which is essentially controlling what will your PC be updated with. Either PC plus 4 or PC plus 4 plus, you take the offset, you shift it left by 2, that is multiplying by 4. You do all of those business here, right? Shift left by 2, add, all of that is being conducted over here. To compute what? To compute the branch address. That is going to eventually come here. So PC source is picking one or the other. Is it PC plus 4 or PC plus 4 plus offset times 4, which is your branch address. So that's happening over here, and that depends on PC source. Let me ask you guys this. In which, there are 5 stages, right, of the instruction. Fetch, decode, let me call it the other way. Instruction memory, register access, ALU, data memory, and write back. Of these 5 stages, in which stage do you actually know the branch? Where is the branch being evaluated? Where is branch being evaluated? Essentially, when do you know which, for sure, which instruction to work on next? After the ALU. Okay, so after the ALU, right here. Yeah, after the execute stage. So what is that? That is your memory access stage, or we are calling it data memory, right? DM stage. That's when you are making the decision. That's when you know whether you want to branch or not. So essentially, you look at this output, if that is 1 or not, right? So for that, two things have to happen. What is that? The branch control signal has to be a 1. You already had that. You already had that information. You already had that information from earlier, because the moment you decoded it, you knew whether you are branching or not. So that was not something that we were waiting for, but we had to wait for this guy, right? We had to wait for 0. Compare the two instructions, subtract them. If they're equal, the 0 will be 1. So we had to wait for this guy. And because we had to wait for this guy, our branch was evaluated late. Now, what is this? Let me number this. Let me number this 1. This is say 2. This is say 3. This is say 4. This is say 5. Right? I'm numbering those 5 stages. I am evaluating branch in 4. Right? Step 4. At that time, how many different instructions have already started coming in to my pipeline? How many? 3 instructions have already come in. There is one instruction which is in this, and this. There is one instruction which is here and here. There is one instruction which is here, right? So 3 instructions have already come into the pipeline. Uninvited guest. Yeah? I don't know. We may need to work on them, or we may not need to work on them. So one idea you can do is this. One methodology is this. Let us try to change our data path a little bit. Essentially bring this a little bit before, right? Like try to make that branching evaluation earlier. That is one way to reduce the number of instructions that you have sort of wasted, right? You may need to flush out of the pipeline. That's one idea. The other idea is, where was I going with this? Lost my train of thought. Okay, let's see. So bring the branching ahead of time. That is one. Yeah, no operation. I had a. All right, it'll come back to me. Anyway, let's try to see this control hazard. How much time are we losing? So we have this add instruction here. After that, we have a branch when equal instruction here. After that, we have a load word instruction over there. So depending on this branch when equal instruction, we may need to work on load word, or we may not need to work on load word. We may actually branch and then start executing what? PC. Oh, this will tell you that, what is that? For 160, right? Because for branching instructions, the offset is in words. So you compute, multiply by 4, you get it in bytes, and then you add PC plus 4. So branch there are two options for the next instruction. After the branch is executed, you may need to work on this, or you may need to work on an instruction at PC plus 4 plus 160. You don't know it. So when is it evaluated? We just said that the branch is evaluated after the data access stage, the fourth stage, right? But until then, the load word has already come in, right? The load word, you have already started working on the load word. You have gone through the instruction fetch, you have gone to the register access, you have gone to the ALU. All of this has happened already for the load word instruction. But if you decide, so that's what, 6 nanoseconds, you have already worked on it. But if you say, let us not work on it, let every time you have a branch when equal instruction, let us not put anything into the pipeline. We are essentially trying to evaluate how much time do we lose. So if you make that decision over here and then only start working on the next instruction, you would have lost 6 nanoseconds. 2 nanoseconds, you have to lose that anyway, because the resource is not available. The instruction memory is not available. But then after that 6 nanoseconds, you have lost, right? So that is idea one. Stall until the branch when equal is decision is being made. But the cost of that is 6 nanoseconds. Each clock cycle, we are using that as 2 nanoseconds, right? So 2 here, 2 here, 2 here. Each clock cycle is 2 nanoseconds. So that's equivalent to 3 cycles. 3 cycles you have lost. So the question is, can we do better while being less conservative? We are now being very, very conservative, right? We are making sure that the next instruction we work on is exactly the right instruction. Go ahead. Yeah, we do. So ALU zero signal is available, but this in our data path has been placed after. So this zero result is written onto the whatever this is, EXMEM pipeline register. Then you read from it, that goes into the AND gate. So the AND gate in our data path is already over here. So one way to do this is probably moving this up. But we cannot just take the hardware and put it up, right? Like you cannot move the hardware. However, you can, okay, now it's coming back to me. However, you can use a different technique to make that evaluation. For example, whenever you're doing this branch when equal, we are talking about two registers, right? The contents of them you have read here and here. What if we put a comparator over here? We put a comparator right here in hardware. And if they are both equal, we would have made that decision right here instead of waiting until there, right? So that is also there, but we can put in a new comparator right here to make that decision early. Can I see that? So yes, that's one way of solving the problem. We still will have a penalty though, because now we are making the decision in 4, so we lose 3 instructions that follow. If we make the decision in 2, we lose 1 instruction that follows, right? Because 1 instruction might still jump in. So the branch penalty, instead of it being 3 clock cycles, it will be 1 clock cycle in that case. So that's actually where we are going with this. So that was 3 clock cycles here, right? Because we were in 4, 3 to 1 would have already been used. You see, 3 to 1 would have already been they would have come in. So let's see. Over here, what do we have? We have address over here, address of where the instructions are. You have a branch when equal, then and or add, and then you have a load word instruction. There is a typo on this slide. Help me figure it out. It's with respect to the branch instruction. Absolutely. That needs to be 7 instead of 28. So branch when equal 1 and 3, and if they are equal, you go to that branch address, PC plus 4 plus whatever, 7 times 4. So PC is what, 40. So you do 40 plus PC plus 4 times 7. You get your 72. At 72, you have a load 1 instruction. So two things could have happened with branch when equal. If they are not equal, so what are those two things? One, $1 equals $3. $1 doesn't equal $3. Go ahead. When do you know the possible branch address? I think it is still in the 80 plus 4. Okay, so it's still over here. Execute stage, right? So it's right. Oh, you know it over here. The next instruction for um, the branch instruction to the next one, meaning the instruction before the branch, after the branch, right? After the branch, yeah. Yeah. So you are talking about, I think, the last slide of my lecture. So there are actually three ideas about that. One of them is what you're calling it is target, from the target. So branch instruction or any condition, they have a target address, right? Branch address. Now you're losing one instruction is penalty for sure, right? Right now we are at the start of this lecture and we have sort of already connected all the dots almost. 3 clock cycles is the penalty now with the current hardware. But if you were able to put a comparator over here and make this decision, make this addition earlier, then you could have got that down to 1. So you could have got that branch penalty down to 1 clock cycle. But that you cannot avoid. 1 clock cycle is going to be there. Now, you can do two things with that penalty. One, no operation, stall the pipeline, do nothing there. Or a better option could be what Peter just said. Use something from the target and put that into the pipeline, because you know you're going to have to work on it anyway. That works in certain scenarios. The other is you can bring in an instruction before the branch and put it in that delay slot. We call it a delay slot. Or there is a fall through after the if condition. There's the instruction after that. Bring that into the delay slot. So there are three ideas, three examples about how do you make the efficient use of delay slot. That has to do with, that also has to do with what is the probability of branch being taken and the probability of branch not being taken. So in certain scenarios, one works. In certain other scenarios, the other option works. So compiler can help, a compiler rearranging the code can help with that. All right, so that's good. You guys have already finished the lecture for me, but we'll continue. Here, so we have got this instruction over there. We have started working on it. We made the decision over here in the 4th stage. But by that time, you would have already started working on and is here, and is here, here, and here. Or by that time is here and here. Add is here. So you have 3 instructions already in the pipeline by the time you make the decision for the branch when equal. So 2 things can happen with this branching. 1 equals 3, 1 doesn't equal 3. If 1 equals 3, then we have to flush out all these 3 instructions. If 1 doesn't equal 3, no problem, you keep going. But do you guys agree that there is some probability with this, some history of conditions, conditional statements that plays a role in this? Sometimes it can happen, sometimes you don't take a branch, right? So for example, when you do a for loop that runs for 100 iterations. Well, for 100 iterations, it is not taking the branch, right? It's still there. Only once it will take the branch. It'll go out of the loop, only once. So there's a lot of that is why you can afford to go wrong, because you're basing it off of probabilities instead of just losing the 6 nanoseconds, instead of just saying, all right, I'll just wait for the whole time that I don't know which one to work on. So proceed assuming branch is not taken. That's what we are doing over here. If you proceed without proceed assuming branch is not taken, then you have already worked on these 3 instructions, right? You have not taken the branch. You have put in all those 3 instructions. But what if we are wrong? If we are wrong, then we flush out these 3 instructions over there. You guys agreed that we need to flush out these 3 right here? It's not 2, it's not 1, it's not 4, it's 3, exactly 3. The reason for that is we have made the decision for the branching over here in that stage. With the current hardware, we have made it over here. We can have a modified hardware later on, but current hardware, we have made it over here. And by that time, we have got 3 instructions in stages 1, 2, 3, or 2, 3, 1, 2, or just 1. So we need to flush them. We need to change all those 3 instructions to NOPs. What is a NOP? We know that it's an instruction with all 32 zeros, right? And if you look at all 32 zeros, it actually is shifting logical left. Shift logical left of register 0 by 0 amount. So it's shift. You cannot write to $0 anyway, but it is shifting a bunch of zeros left by 0 amount. So it's like, so it stays the same. That's how you execute NOP. Let's see. So we need to flush out all these 3 instructions from the pipeline. How do you flush them out? You set the control signals to 0 for the 3 instructions. One is IF, ID, EX, IFID, IF. So all these 3 stages, we are going to set the control signals to zeros to flush those 3 instructions out of your pipeline. And then from here, you work on the next instruction, which is your load word instruction. This is when you are actually taking the branch. That's how you would flush them out. So the cost of cycles lost during flushing is what? That's what we are calling it a branch penalty. And the branch penalty is, with the current hardware, it is 3 clock cycles. So what is the average cost of guessing branch is not taken and being wrong? What is the cost of being wrong? Well, you will have to look at it in terms of a statistic. Probability that the branch is taken multiplied by 3 cycles. Why 3 cycles? Because every time you are wrong, you will flush out 3 instructions. So for example, if the probability of a branch being taken is 0.4, 40% of the time you're taking the branch, then you have a reduced cost from 3 cycles to 1.2 cycles on average. Because 60% of the time you're not taking the branch, so you'll be fine. There's no penalty over there. You guys are seeing how things are going so far? 3 cycles is the penalty. And if you associate probability with branch taken versus branch not taken, say we have a probability, this is just an example here. Probability of branch being taken, if it is 40%, then only 40% of the time we are actually going here. 60% of the time we can follow through on our instructions and not have to pay any branch penalty. So effectively, our clock cycles that we lose as branch penalty come down from 3 to 1.2 because of that probability being 40%. If we could reduce the amount of flushing needed, then we can actually lower this even further, meaning we can try to lower this 3. We cannot do anything with this, right? Probability of branch taken, not taken, it might not be 0.4, it might be some other number, but that is specific to the instruction. We cannot change that, but you can play with this, right? We can try to reduce this 3 by making the decision early, right? It was 3 here, because we were making the decision in clock cycle 4, and our new instruction was already coming in into clock cycle 1. So the difference over there was 3. Let us try to see if we can make that branch evaluation earlier. Reduce the penalty. So here, we have already talked about this. This is where we made the branching instruction based on the ALU result. Question is, can we make it earlier? Put a comparator over here. Immediately after the register file, when you read those two registers, branch when equal requires you to read those two registers. Once you read those two registers, put a comparator over here. And if the comparator is comparing two 32-bit numbers, and if the comparison says that they are equal, then you know already. You don't need to wait over here until here. You already know that those two are equal. So instead of making the decision in stage 4, now you are making the decision in stage 2 by moving the comparator over there. So that's your modified hardware. You are moving up the branch evaluation, but alongside that, you also have to move up the calculation of the branch address ahead of time. It was earlier over here in stage 3. Now we are moving that into stage 2. So we have two things over here. Comparator came in, and the address calculation, the branch address calculation moved up from stage 3 to stage 2, from execute stage to the register access stage. Now, our cost has gone down by how much? From 3 to just 1, right? So 1 is the branch penalty now. On average, again, if we put in those probabilities, it is 0.4. 0.4 clock cycles that we lose on average. That is okay, but we can still reduce it. If we are doing the branch, now how do you actually do the branch? Right? We have talked about moving things up from stage 4 to stage 2 for the comparator, and from stage 3 to stage 2 for the ALU, adder. Not the complete ALU, just the adder that evaluates PC plus 4 plus offset. However, when there is that, when we are actually branching, suppose we are wrong. If we are wrong with the branching, we need to still flush out one instruction that has come in. How do you flush it out? If we are wrong, we need to flush it out. The way you flush it out is, again, you have that hazard detection unit, which is going to detect whether you have to, if we are doing the branch and the registers are equal, those are going to be two more inputs to your hazard detection unit. And if it is true, if we are doing a branch and if the registers are equal, the connections are not being shown over here, right? The output of the comparator is functioning as the input over here. If the registers are equal and if you are doing the branch, the branching is fine. The branching is essentially going to come from the control unit to the hazard detection unit if you are doing the branch. You guys agree with that? Branching is one of the control signals that gets decoded, right? So that information is available from the control unit itself. But if the registers are equal or not, that is going to be the output of the comparator. So those two things are going to function as input to the hazard detection unit. And if that is true, if you are branching and if the contents of the two registers are equal, then you simply make the instruction that you just fetched, the flush signal for that, set to 1. And by setting it to 1, you are essentially, you're setting this to 1. And by setting it to 1, you are essentially saying that right now, whatever my instruction is over here, I'm going to make that irrelevant. Whatever instruction is in the IFID pipeline register. So one instruction that immediately follows the branching instruction. So if, IF stage, the flush signal, if it is set to 1, that essentially means the instruction that you just fetched, the next one, the one following the branch, change that instruction to a NOP. And the way you change that to a NOP is make all of these 32-bit instruction go to zeros. All 32 zeros corresponds to a knob, which is actually shift logical left, register to register 0, register 0, register 0, meaning you're essentially doing nothing there, right? Which does nothing to register 0, which couldn't have been written. We cannot change the contents of $0 anyway. So that's your modified hardware. With modified hardware, your branch penalty is what? 1 clock cycle, right? 1 clock cycle is still the branch penalty. Questions so far? The earlier hardware, branch penalty 3, with the probability comes down to 1.2 for some arbitrary probability. With the modified hardware, what is modified hardware? You have moved things up in terms of branch being evaluated and in terms of address being calculated. You have moved things up to stage 2 in the register access stage. By doing that, you have brought down that branch penalty from 3 cycles to 1 cycle. With the probability of branch being taken or not taken, you can still go down to, say, for example, 0.4 clock cycles on average. And if the branch penalty, the way you pay it, if you are wrong, is by flushing out one instruction, the instruction that immediately follows the branching instruction. And the way you do that is by setting it all to zeros. The hazard detection is going to check for 2 things. Is it a branch instruction? Are the register contents equal or not? How does it know whether it is a branch instruction or not? It is going to be one of the outputs of the control unit. How does it know whether they are equal or not? Output of the comparator. If those 2 conditions are satisfied, set this flush signal to a 1. And if that is a 1, you essentially take the instruction which was immediately after branch and make it all 32 zeros, which corresponds to this new operation. That does nothing. Yeah? All right. So what is the benefits of modified hardware? We go down from 3 clock cycles to 1 clock cycle. Reduce the branch penalty only whenever you are wrong. When you're right, there's no penalty. Down to 1 cycle from 3 cycles, right? So let's try to predict the branches. So let's say our prediction can happen one of 2 ways, right? You can say, I will predict that the branch is always taken. Or you can predict that the branch is not taken. So if you predict that the branch is taken, then the next instruction that you need to update your program counter with will be this: PC plus 4 plus sign extended offset multiplied by 4. And you guys know why you need to do the sign extension, why you need to do the multiply by 4, and why do you need to add that PC plus 4. You have seen all of those things. So the branch destination would be this, if the branch is taken. Branch is not taken, then our PC will be updated with PC plus 4, immediately the next instruction. So those are the 2 options that you have for predictions, one or the other. Now, the result can be either a correct prediction or incorrect prediction. If you have a correct prediction, then you don't have any branch penalty. Branch when equal takes 1 clock cycle like all the other instructions. But incorrect prediction, you need to flush out the pipeline, which takes 1 extra cycle with the modified hardware. Otherwise, it would take 3 clock cycles. Now let's take a look at ways to predict. One way to predict, how would you predict? So suppose you have something, you don't have a history, right? So suppose you don't know historically what is the probability of branches being taken or not taken. You don't know that. How are you going to predict what you need to do? One strategy, let me lay out the simple strategy here. I will start off with some assumption, okay? I will start off with an assumption that branches are always taken. Branch is there, it is always taken. If I start off with that assumption, I can keep doing that until it is actually true. The moment I'm wrong once, I will change that prediction to the opposite. Branch is always not taken. And I will stay there. I will continue doing that until I go wrong. If I go wrong, immediately I will change. Reasonable, unreasonable, slightly better option, which actually gives you 90% accuracy. I'll start off with one assumption, and I need to go wrong twice before I actually change it. So I'll start off with one, say branch is always taken. I will not change to branch is always not taken, branch not taken immediately after I go wrong once. I have to go wrong twice to change it to branch is not taken. So again, I have two versions because I need a starting point, right? Like I need a starting assumption, branch is taken or branch is not taken. Those are my two versions. Version 1 is assumes branch is taken. Version 2 is assumes branch is not taken. But with this, I will have 4 different states. I'll start making a state diagram with this. Why do I need 4 states? Because I'm not just in 2, right? I'm not jumping from taken, not taken, taken, not taken. I'm actually jumping from taken to maybe, but I'm still taking it, and then not taken, right? I'm using 4 states there. Fact 1 and fact 2, these are historically known, which is sort of helping us with the prediction. Branch when equals instructions in loops are taken often. And branch when taken equals for testing rare cases, for example, errors, are rarely taken. So these are the 2 things that are going to help us do that prediction. The bottom line is this: it is skewed one way in both of them, right? If your predictions are skewed one way, then because of that being evaluated on average, the penalty goes down. So ways to predict: number 2, dynamic prediction. Keep a history table of all the branch instructions, depending on branch taken or not taken. And then based upon the history, you do that prediction. And the idea is prediction must be wrong twice to change to the next prediction. You need to go wrong twice in order for you to change your assumption, starting assumption. So let's take a look at that in terms of a state diagram here. You have 4 states. Let me call them state 0, state 1, state 2, and state 3. I'm arbitrarily assigning them 4 names. In the ones that are highlighted in blue, the prediction is that branch is taken. And the ones that are highlighted in gray, the prediction is branch is not taken. So if you are, say, in S0, and you keep coming across situations where the branch is taken, you will stay in that state where you assume that the branch is taken. However, if the branch is not taken once, the first time, you go to the S1 state. From the S1 state, if you encounter a good thing, right? Like if you encounter a taken, you come back. But if you go wrong once and you go wrong twice, then you start looking at maybe it is better to assume the other thing. Predict branch is not taken. That is S2. And if as long as that is the case, you stay there. If you go wrong once, you come here. If you go wrong twice, you come back over here. This gives you a 90% accuracy. And we have only one thing. Why do you predict? Why do we need to predict branch? Well, if we don't predict branch, then we are losing 1 clock cycle, right? And we are trying to reduce, on average, even that 1 clock cycle. So let's suppose that half the time branch is taken, half the time branch is not taken. If that is the case, then we lose that 1 clock cycle whenever there is a branch instruction half the time, and we don't lose it half the time. But that's not the case, right? That's not reality. The reality is, if you look at fact 1 and fact 2, the branches are skewed towards one end or the other end. Loops, often it is taken. Rare cases, rarely taken. So because of that skewed nature, it's not half and half anymore. If it was half and half, then we don't gain anything from prediction. Because of the data being skewed that much, you can start predicting so that the one clock cycle that we lose is actually maybe like 0.1, right? Instead of one clock cycle. So I hope that answers that. All right, let's go forward. Rearranging the code. You guys have already helped me a little bit with this. A delayed branch. Essentially, a delayed branch is what? You have a branch when equal statement. The instruction immediately after that is going to be in the pipeline. It may be the correct instruction or it may be the incorrect instruction to work on. But that one instruction is referred to as a delay slot. The compiler can rearrange the code so that the next instruction is always executed, and the location is called the branch delay slot. So we can do some rearrangement such that the next instruction, instead of it being a knob, it can actually be something that is useful. Let's try to see some ideas. Example 1. Peter's option was one of these. It was from the target. This one is, now some of these, it's not tied to one prediction, right? It's in some cases, the strategy works for branches not taken. In some other cases, it works when prediction is branches taken. Here, example A actually works for both. You have a delay slot immediately after the condition, if condition over here. You have some add instruction that was before the branch instruction, before the equal instruction, before the if condition. After the if condition, you have that delay slot. The instruction immediately after that is what gets impacted. So one option is take the instruction before the branch and move it into the branch slot. Take the instruction before that, move it into the branch slot like this. This becomes that, right? Now you know that the branch is going to be evaluated. The next instruction is going to already enter into the pipeline. But because this is something that is independent of S2, well, you're checking over here if S2 equals 0 or not. But this one, you don't care, right? You're taking S2 and S3, adding it and putting the result in S1. There's no relevance over there. You can actually completely work on this instruction. You don't need to lose it. You don't need to flush it. So that's one example. This is the best way when it is possible. So whenever this is possible, you try to use example A. This is called from before. This is from before branch or condition. Take an instruction from before the condition and put it in the delay slot. The next example is from, let's see, this is the target, from target. This is what Peter was talking about. On the left over here, we have some code. We have a subtract instruction. Then we have some instructions. Then we have an add instruction here. Then we have a condition that checks for S1. And after the condition, you know there is a delay slot. So clearly, we cannot move add over here, right? The reason why we cannot move that over here is because S1 and S1 over here. You're changing S1 and you're checking S1. You cannot change that order anymore. But what you can do in this case is the target of the branch instruction is over here, right? You can move the target into this. When can you do this? You can do this if you are assuming that the branch is always taken, right? So if you are in that model, if you are in that prediction model where branch is always taken, then you know that immediately after this, the branch is taken, right? So you are going to execute this subtract instruction. If that is the case, you just bring that subtract instruction into the delay slot, right? So this works really well when the prediction is branch is taken. And it's called from target. Whatever you have at the target, right? Target of the branch, that instruction is moved into the delay slot. Next. This is from fall through. So you have the add instruction, then you have the condition, you have the delay slot over here, and you have the subtract instruction over here. What are we doing? We are taking the subtract instruction and we are moving that into the delay slot. Again, we cannot move add because S1 needs to get updated and be checked. We cannot move add. But this subtract can be moved over here, and this will work when subtract can be executed for both outcomes, branch taken and branch not taken. So these are some of the options that you have while the compiler is rearranging the code to even save that one clock cycle that could get affected. All right. That is all we have for today. You guys have a lot of time for the activity. Homework 4 has been posted. So homework 4 is about pipelining. It's an interesting homework that's due Monday of next week. So you have that to work on, and you have the activity for today to work on. All right. Stop the recording here.